Let's take a look now at two events. The event A occurring or B occurring, or possibly them both occurring at the same time. So we would donate this way, the probability of A or B. And I've identified in this example what A is going to be. So in the deck of cards, A is going to be a heart, and B is going to be a black card. So what's the probability that I take a deck of cards, pull one card off the top? What is the probability that it's a heart or it's a black card? Something that'll help us to see what this is would be to draw a little box. Let's say this box represents all of the 52 cards in the deck. Here would represent event A, all the hearts. Here would represent event B, all the black cards. Notice in this example that all of the hearts and all of the black cards are completely separate from each other. You can't have a heart that is also black since the hearts are all red. So there are 13 hearts in the deck, and there are 26 black cards in the deck, and 13 cards that do not belong in this circle, the circle of hearts, or in this circle, the black cards. So in our example, these two events, event A and event B, are what we call mutually exclusive. And what we mean by mutually exclusive is that event A and event B are completely separate from each other. Or in other words, the probability of A and B occurring is 0. You cannot, in this deck, pull a card out and get one card that is a heart and is black. Hearts are not black cards. There's no cards that are the same. In our next example, we will look at some scenario where event A and B can occur at the same time. So let's go back to this example. The hearts and the black cards are completely separate. So if that is so, then the probability of A or B occurring is simply equal to the probability of A plus the probability of B. The probability of me getting a heart is 13 out of 52 plus the probability of me getting a black card is 26 out of 52 for a grand total of 39 out of 52. So the probability of me drawing a heart or a black card is 39 out of 52. Again, there'd be 39 favorable outcomes. There's 39 cards in that deck that are either hearts or blacks out of the total of 52. So very important that we understand that when events are mutually exclusive, there's no overlap. A and B are completely separate from each other. You cannot have A and B occurring at the same time. That probability would be 0. And if that's the case, then the probability of A or B, I simply add the probability of A plus the probability of B together. Let's look at one more example that's mutually exclusive. Let's say our sample space represents all of the people that make up a school. So within a school, you would have grade 8, 9, 10, 11, 12 students. You'd have teachers, you'd have administration, you'd have secretarial staff, you'd have custodians, all the people that would be in the school. Now let's just say what would be the probability that if we randomly selected someone out of the school population that they would be either a teacher or a grade 10 student. So if we look at this box and say this box represents the school, then we would have event A over here, which represent all the teachers, and we would have event B over here, which represents all the grade 10 students. And I think it's pretty safe to say that there are no grade 10 students in a school that would also be teachers. So they would be mutually exclusive events. And all the people outside of these two circles would represent all the other students in the school, all the administration and custodial staff, secretarial staff, and so on. So the probability of A or B would simply be the probability of A plus the probability of B. And so what would be the probability of selecting a teacher? Well, let's just say there were 50 teachers in a school of 1,000, and let's say there were 150 grade 10 students in that school of 1,000, for a total of 200 out of 1,000, or in other words, there's 200 people in the building that are either grade 10s or teachers, and we could reduce this to 2/10 or 1/5. So the probability of selecting a teacher or a grade 10 student in the school would be 1/5. Mutually exclusive events. A and B completely separate. So the probability of A or B is just equal to the probability of A plus the probability of B.
Two events are mutually exclusive if they cannot occur at the same time. In other words, the two events are totally separate from each other. Here you can see that events A and B are mutually exclusive. They are separate from each other. An example would be event A is a spade and event B is a red card. Since no spades are red cards, those two events would be mutually exclusive. For mutually exclusive events, the probability of A or B is equal to the probability of A plus the probability of B. And the probability of A and B will always equal 0 since the two events cannot occur at the same time.
So now let's consider this example. Again, it's what is the probability of event A or B occurring? And I'm going to say this time that in a class of 30 students, so pretend you're in your math class, what is the probability that a student in the class is taking biology 12, or what's the probability that they're taking physics 12? So imagine this is our classroom, 30 students. So in the classroom, I say I want all the people who are taking biology 12 to go stand in this circle. So you imagine some people get out of their desks, move around, go in this little circle here. These are all the biology 12 students in the class. Then I ask people, all right, I'd like everybody else, or I'd like anybody who's in physics 12 to go stand in this circle. Well, there'd be some people here who weren't taking biology 12 who would go stand here, but probably there'd be a few students in this circle saying, well, hold on here, I'm taking biology 12 and physics 12. So what we have is a situation here where these are no longer mutually exclusive. There are some people who are both in biology 12 and physics 12. So our two circles might look like this. And then this part here, students in this little spot right here, are taking biology 12 and physics 12. So let's look at our little Venn diagram. We call it Venn diagrams here. People that are just sitting here in this part of circle A, these are the students who are only taking biology 12. A taking biology 12. Students over here in this part of circle B are the students that are just taking physics 12. And then we've got a few people right here, probably not too many, but a few that would be in both circles. They're both taking biology 12 and physics 12. And then everybody else in the math class who aren't taking biology or physics would be out here. But everybody in this box represents all 30 students that were in that class. So now, if I said, all right, let's put some numbers in here now. Let's say there were 10 students that were taking biology 12, and let's say there were 9 students who were taking physics 12, and there were 3 students who were doing both. Okay. So now if I want to find the probability of A or B, I'm going to add all the people in A plus all the people who are standing in B. But when I do that, I'm going to end up counting these people twice. Let me give you an example here. So say we've got our students sitting here, standing here, students standing here, and the students who aren't in either there. So I say, how many people are taking biology 12? And those students put their hands up. I count all those students. Now I say, all right, I want all the students taking physics 12. And all the physics 12 people put their hand up. And I count all those. The problem would be is that I've counted these people twice, because they put their hand up when they were taking Bi 12, and then they put their hand up again when they were taking physics 12. So I need to subtract the probability of A and B. I need to subtract these overlapping people because I would have counted them twice. So the probability of A or B would be equal to the probability of A. There are 13 people who are in the A circle, plus, that's 13 out of the 30, plus there are 9, 10, 11, 12 people standing in the B circle, so 12 out of the 30, minus these 3 people out of 30, because I've just counted them twice. And so 13 out of 30 plus 12 out of 30 is 25. 25 minus 23 is 22 out of 30. So the probability in our math class that students are also taking biology 12 or physics 12 would be 22 out of 30. So this formula here is the formula for finding the probability of A or B. Probability of A or B is the probability of A plus the probability of B minus the overlap, that's the probability of A and B. And of course, if there is no overlap, in other words, if they're mutually exclusive, then this probability is 0, and so that disappears. So this is really the only formula that you really need to know for finding the probability of A or B.
If A and B are two events that are not mutually exclusive, then the probability of A or B will equal the probability of A plus the probability of B minus the probability of A and B.
"50% of people like Chinese food, 30% of people like Italian food, and 20% like both. What is the probability that a randomly selected person would like Italian but not Chinese?" Draw a little picture. Always helps. Okay, so there's people who are liking both, so these are going to overlap. They are not mutually exclusive. Let's make this one the Chinese food, this one the Italian food. Oops. This one the Italian food. So I've got 50% of people liking Chinese. I've got 30% of people in the Italian circle, and I've got 20% of people in the middle liking both. So this question says, what is the probability that they like Italian but not Chinese? So I want this area right here. I want the people who are standing in the Italian circle, but not this part of the Italian circle, because if they're standing here, they're also in the Chinese, and these people are not supposed to like Chinese food. Well, if you've got 30% in this whole circle and 20% standing here, then this probability would equal 30% minus 20%, which is 10%. So the probability that they like Italian but not Chinese would be 10%. You see how easy it is to find the probability when we have a little diagram drawn. Let's consider the same example, but this time we're going to ask the question, what is the probability that they like neither Chinese or Italian? So they're not going to be standing here because this is just Chinese, and they're not going to be standing here because they'll like Italian, and they're not going to be standing in the middle because they'll like Italian and Chinese. We want the people who are out here. Well, we know that if this box represents our entire sample, our entire population, then this got to be 100% of the people. So what we need to do is we need to determine what is the percentage of people who are in these circles. We want to find out what is all of that area. Okay, so that probability that they like Chinese or Italian, probability that they like Chinese or Italian would be 50. All the people standing here, 50, plus 30, all the people in the Italian circle, minus the overlap, because we would have counted those people twice. 50 plus 30 is 80. 80 minus 20 is 60. So we've just figured out that there's 60% of people that like either Chinese or Italian food. Now that's not our question. The question is, what's the probability that they like neither? Well, remember the complement? If we've just found the probability that they like Chinese or Italian, then the probability that they like neither should be 100%, all of them, subtract the 60, which is 40%. Again, fairly easy to determine by our little diagram that we've drawn. So 40% of people are outside, 50% of people liking Chinese, 30% liking Italian, 20% liking both.